Okay, so in this video we want to introduce matrices. So matrices is actually no longer a big part of the methods course at all. They greatly cut it down at the last study design change, but they left enough of it in that we still do need to teach you the basics of matrices. Now, in the past we've taught this in much earlier year levels, and you've at least come into methods knowing this, but we haven't had the opportunity to do that. So we need to cover some basics of matrices. The basics are not complicated. The multiplication is a little tricky, and we do need to get our head around these basics in order to be able to utilize matrices in the context of transformations, which is essentially the only place that they remain. And that requires an understanding of matrix multiplication, that requires an understanding of how matrices connect to simultaneous linear equations, but other than that, you're not going to get specific questions on matrices. There is another application where matrices can be useful, and that's around simultaneous equations and matrices, and the next couple of videos will look at that in a little more detail. But there are other ways to solve similar problems, but those kind of problems that we'll look at do continue to come up. Anyway, so today we want to introduce matrices. Many of you will never have met a matrix before. And essentially a matrix is a rectangular array of numbers. That's a technical definition. It is basically a list of numbers in a grid, or a table of numbers in a grid. Okay. Matrices are usually denoted by capital letters, which if typed are often written in bold text. And the size of a matrix is referred to as its dimension or order. Okay, and that would be written like a product. So an m by n matrix has m rows and n columns. So for example, here, this matrix we see here, that is a 2 by 2 matrix. It has 2 rows and 2 columns, and so it is 2 by 2. This matrix is a 2 by 3 matrix, 2 rows, 1, 2, 3 columns. Okay, 4 by 1, 1, 2, 3, 4 rows, 1 column, and 1 by 4, 1 row and 4 columns. Now the numbers can be whole numbers, decimals, fractions, positive, negative, zero, surds, pi, rational, irrational, all those things. Okay. It's essentially a big data storage thing. Okay, so matrices, you know, are really fundamental to a lot of modern day maths in terms of that sort of analysis of big data and being able to work with matrices, but that's not really what we're kind of looking at here. We're looking at a very niche application. Okay, so some other basics. Two matrices are equal if they are of the same dimension and if all corresponding elements are equal. So for example, these two matrices are if these two matrices are equal, they're obviously of the same dimension, so that's covered. But from that, if we know that they're equal, we can therefore infer that x has to equal 21, and we can also infer that y has to be equal to 15. Okay. All right. Entering a matrix with your CAS. No, we're not entering the matrix with Keanu Reeves, but entering a matrix into our CAS. You're probably not going to have huge need to use your CAS with matrices. However, obviously just worth being aware of the fact that it can work with matrices. So there is a matrix menu. So menu number 7 is the matrix and vector menu, and then you could click create a matrix, create number 1 matrix. And then define how many rows and columns you want. I wouldn't usually do it that way. The quicker way to access matrices is via the template palette, which is this button next to the number 9. If we click on that, there are 3 different boxes here, which are all to do with matrices. So these, sorry, 4. These first 3, this would bring up a 2 by 2 matrix template. This would bring up a 1 by 2 matrix template, a 2 by 1 matrix template, and then if you choose the 3 by 3 looking matrix template, again that will be where you can define a matrix of a different size. But you've got those sort of shortcuts for just a 2 by 2 matrix if you want to, if you need to access those. So you know, and then quite literally you just enter the numbers into the boxes, and there you go, you've got a matrix. Okay, matrix addition and subtraction, very, 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 very easy. So yes, our CAS can do it just by typing in one matrix and pressing the add button and then typing in another matrix, but the time that it took you to do that, you could do it quicker by hand. If we're adding two matrices, we can only add matrices if they are of the same dimension. So if they have different dimensions, they're a different size, they can't be added. And if they're of the same dimension, we add the matrices simply by adding corresponding elements. So 16 plus negative 12 gives 4. Negative 5 plus negative 2 gives negative 7. Okay. Negative 3 plus 15 gives 12. And I've run out of different highlighter colours straight in my palette, but here we go. 12 plus 8 gives 20. Okay, so simply adding the corresponding elements. Same if it is subtraction, simply subtracting the corresponding elements. So here we've got, 4 minus 6 is negative 2, and negative 1 minus minus 2 is negative 1 plus 2, which is 1. So nice and easy. Matrix multiplication of a matrix by a scalar. So a scalar is another way of referring to a constant value, or a numerical value, I guess, but a constant value, if we multiply by any real number. So, and if we're multiplying a matrix by a number, we simply multiply every element in that matrix by that number. So here, for example, we are doing 2 times this 2 by 3 matrix, and so all we're doing is doubling the 6 elements in the matrix. Okay, so 2 times 3 is 6, 2 times 0.1 is 0.2, 2 times negative 1 is negative 2, etc. Okay, so nice and easy, nothing complicated. Then we get into matrix multiplication. Now, matrix multiplication is significantly more complicated than matrix addition and subtraction and multiplication by a number. So here, when we say matrix multiplication, we're not multiplying a number times a matrix, we're multiplying two matrices. Okay, so just some language too. Just matrix is a singular thing, so we have one matrix. But if we have more than one matrix, we have two matrices or three matrices. So plural of matrix is matrices. So the product of two matrices only exists if the number of columns in the first matrix is equal to the number of rows in the second matrix. Now that seems a complicated thing to remember, but once you know how to do matrix multiplication, it will quickly become very apparent to you when the multiplication is not possible. However, the other way we can think about it is when we write out the dimensions of our two matrices, if we're doing an m by n matrix times an n by p matrix, so the first matrix has m rows and n columns, and the second matrix has n rows and m columns, it's all about, the condition for multiplication is all about these two numbers in the middle here. Number of columns in the first matrix has to be the same as the number of rows in the second matrix. So if when you write out the order of the two matrices, and obviously in the order that you're going to multiply them, if when you write them out these two inner numbers are the same, then the matrix multiplication will be possible. Whereas here, an n by p matrix being multiplied by an m by n matrix, so all we've done is reverse it, do the matrix multiplication in the reverse order, is not going to be possible because the number of columns in the first matrix does not equal the number of rows in the second matrix. Okay, so we cannot do that multiplication. If A is an m by n matrix and B is an n by p matrix, then AB, so that's when we do this, m by n times m by p, and it's possible because of that. But the matrix that we end up with will be an m by p matrix. So the two middle numbers, when we write out the two orders in order, the two middle numbers must be the same in order for the multiplication to exist, and the size or dimension of the matrix we'll end up with is equal to the two outer numbers. So m by p will give us our the size of our matrix. So for example, if we had a 4 by 3 matrix and we're multiplying that by a 3 by 2 matrix, it's possible because of this, okay? And the matrix we end up with will be a 4 by 2 matrix, okay? Third dot point there, in general, matrix multiplication is not commutative, so that is that A times B is not the same as B times A. So we need to be a bit careful about matrix arithmetic. It differs from numerical arithmetic in a number of ways. And we actually saw that here. If we think about this as being A and B, an m by n matrix times an n by p matrix, well, this was B by A, n by p times m by n, and this one's not possible, but this one is possible. So not only will they not equal each other, sometimes the multiplication isn't possible in both directions. In fact, more often than not, it's not possible in both directions. Okay, I've got a loose worded sentence of how we go about multiplication. but this is really something that you need to see. And this is not a mathematically precise word description either. But loosely speaking, to find the product of two matrices, each row in the first matrix must multiply each column in the second matrix. Okay? And as I said, this is a process that needs to be demonstrated. There is a specific matrix multiplication video here. It's a much older video I recorded, but I'm going to go through some examples here, or just two examples. Okay, so we have A, which is a 2 by 2, A, which is a 2 by 2 matrix, and B is also a 2 by 2 matrix. So we can obviously when we have square matrices, that is, the same number of rows as columns, the matrix multiplication will always be possible. If we're multiplying two square matrices, as long as they're of the same order, obviously. A 2 by 2 times a 3 by 3 wouldn't be possible, but any 2 by 2 matrix can be multiplied by a 2 by 2 matrix, and we will end up with a 2 by 2 matrix when we do that. And so that means in this instance, we can find B times A, because if we reverse the order that we do the multiplication, it's still 2 by 2 times 2 by 2. Okay, so we're going to do two multiplications. We're going to do this multiplication in two different directions, and this will also help to verify that even when it's possible in both directions, we won't get the same result. Okay, so A times B, AB is going to be 11, negative 5, 2, negative 3 times negative 1, 6, 9, negative 3. Okay, so each row in the first matrix must multiply each column in the second matrix. I know that's a loose description, bear with me. I'm going to write out a big matrix, so I'm going to write out all the numbers, but you'll get good at doing this, doing a bit of it in your head. Okay, so first row or top row times left column, we're going to need to do top row times left column, top row times right column, bottom row times left column, bottom row times right column. Okay, every row in the first matrix multiplies every column in the second matrix. When we multiply, and I use that phrase multiply loosely, I'll talk about what it means to multiply those together. But when we multiply the top row by the left column, that value that we get is going to go in the top left of our answer. Okay? When we multiply the top row by the right column, that will go in the top right. When we multiply the bottom row, oh sorry, that's a thick pen, let me try a different pen. Bottom row times the I'm just going to do that slightly different. Bottom row times the left column, that's going to go in the bottom left, and bottom row times the right column, that's going to go in the bottom right. Okay, so bottom row times the left column. Let me just get rid of those, all of those for a minute. We'll come back to that. Okay, so sorry, top row times left column goes top left. So what I tend to see in my head, and it's really hard for me to demonstrate this on video because I would be waving my arms around here, is I imagine taking this row and tipping it up around this way, okay? So that essentially, it is 11, 5. So it's also vertical, okay? I don't do it, that's what I kind of see happening in my head. And then I'm going to multiply together these two numbers and add it together with the product of these two numbers. Okay, so it is going to be 11 times negative 1 plus 5 times 9. That's the number that's going to go in the top left. Okay, alright, let me see if I can erase that. Let's put that back. Okay, so now we're going to focus on the top right, and we're going to obtain that when we multiply the top row times the right column. Okay, so again, I'm imagining flipping this around so that it is 11, 5, and multiplying 11 times 6 plus 5 times negative 3. Okay, whatever that is, that will give me my number in the top right. Then we're going to have bottom left is bottom row times left column, and again it's still about spinning it around this way so it becomes 2, negative 3. Okay, so I'm going to write 2, negative 3 and multiply, so it's 2 times negative 1 plus 3 times 9. Okay, again I'm going to lose half my matrix while I get rid of that. Okay, and then the bottom right, bottom row times right column, again we still have to tip it up this way, so 2, negative 3, okay, and I imagine that up here, and I'm going to do 2 times 6 and negative 3 times negative 3. Okay, so it is 2 times 6 plus negative 3 times negative 3. Okay. Alright, so then we can work out what all those things are. So 11 times negative 1, so it's negative 11 plus 45. That's 45 minus 11, so that's going to be 34. This is 66 minus 15, so that is 51. Sorry, it's late in the day and it's been warm. I'm not going to say I won't make a numeric error here. Negative 2 times 20, negative 2 plus 27, so 27 minus 2, that's 25, and 2 times 6 is 12, plus negative 3 times negative 3, so 12 plus positive 9, 12 plus 9 is 21. Okay, let's just verify, because I'm not confident that my arithmetic is very accurate today. Okay, so we can type our two matrices in, 11, 5, 2, negative 3, outside the matrix, multiply by, and then enter in our second matrix, negative 1, sorry, let's get rid of that, negative 1, 6, 9, and negative 3. 34, 51, what did I do wrong with that one? I lost a negative. Sorry, so bottom left was bottom times left, so it should be negative 3 times 9. Sorry, that's my fault. Lucky we checked. Negative 3 times 9. And so that is actually negative 2 plus negative 27, so negative 2 minus 27, which is negative 29. Okay? Alright, let's see if we can replicate that again. It really is, I know it seems complicated at the beginning, but you just need to practice it a few times, and once you've done it yourself a few times, you'll find that it becomes quite intuitive. Well, not intuitive, but it becomes, you learn the process pretty quickly. Okay, so we're doing the multiplication the other way around. So minus 1, 6, 9 minus 3, 11, 5, 2, negative 3. Okay, so again it's 2 by 2. So we're going to have a 2 by 2 matrix. Again, I'm just going to give myself room to write out the calculations. So top left is going to be top row times left column. So that's going to be negative 1 times 11, which is negative 11, plus 6 times 2, which is 12. Okay? And if you can do that in your head and carry all that, fine. But I'm just going to write those out. I'm writing out slightly less than I did in the last calculation. But all the same. Sorry, I lost a number there. What was that? 6. Okay, top right, top row times right column is going to be negative 1 times 5, so that's negative 5, plus 6 times negative 3. So 6 times negative 3 is negative 18. Okay. And then we're going to have bottom row times left column. Okay, so that's going to be 9 times 11, which is 99. Oops, sorry, need a pen. 99 plus negative 3 times 2, which is negative 6. And then finally, bottom row times right column, 9 times 5, which is 45, plus negative 3 times negative 3, so plus 9. Okay. Alright, and then again we should just be able to tidy things up. Negative 11 plus 12 is 1. Negative 5 plus negative 18 is negative 5 minus 18, that's negative 23. 99 minus 6 is 93, and 45 plus 9 is 54. Okay, so again we can check, we can, just going to copy that and delete that and move it to the front. It's a bit fiddly, probably almost as quick to retype it. Do the multiplication the other way around. 1 times 1, negative 23, 93 and 54. Good. Okay, so as I said, just a bit of practice and you'll find that becomes second nature. Summary of matrix arithmetic, there's nothing fancy. If you want to add them, you add. If you want to subtract them, you subtract. If you want to multiply them, you multiply. If the dimensions don't work, it'll tell you that. So here, this is a 2 by 1 matrix, and you're trying to multiply that by a 2 by 2 matrix, and so number of columns in the first doesn't equal number of rows in the second. That's not going to be possible. Okay, so that's why it says error, dimension error. Whereas this one, is a 2 by 2 times a 2 by 1, 2 by 1, so that's fine, and we'll end up with a 2 by 1 over here, as we see. Okay. So when you have that, just to talk quickly about that, remember each row in the first multiplies each column in the second, so top row times the only column goes in the top of your only column of your answer, and then bottom row times only column goes in the bottom of the only column in your answer. Okay, identities. So an identity matrix is a square matrix with all entries 0 except for a diagonal of 1s. And the identity matrix is essentially the matrix equivalent of the number 1. Any number times 1 is equal to itself. Similarly, any matrix times an identity matrix is equal to itself. Obviously, that's provided that you can actually do the multiplication in the first place. So let's just verify that here. So let's again practice a multiplication. If we're going to do this matrix multiplied by a 2 by 2 identity matrix, so it has to be a square matrix, so it can be 2 by 2, 3 by 3, 4 by 4. We won't really go beyond, we do talk a little bit about 3 by 3, but it's mostly just 2 by 2. Okay, so if we do the multiplication, let's see if we can, I'll write it out and then we'll see if we can do it in our heads. So top row times left column goes in the top left. Okay, so it's 3 times 1 plus negative 2 times 0, and so that's just 3. Okay. Top row times right column goes in the top right. That's 3 times 0 plus negative 2 times 1, so that is negative 2. Bottom row times left column. 8 times 1 is 8 plus 6 times 0, so we just have 8. And then bottom row times right column, 8 times 0 is 0 plus 6 times 1 is 6. Okay. So we see that actually when we took this matrix, multiplied it by the identity, we call that matrix A, and multiplied it by the identity, it still equals matrix A. And you can check it, but you would find if you did the multiplication the other way around, if you did the identity times A, you would also just get A. Okay, so you might want to give yourself another matrix multiplication practice by having a go at that. So, useful property of identity matrices, any matrix multiplied by an identity, provided the matrix multiplication can happen, is just equal to itself. It's also a situation where the matrix multiplication is commutative. A times the identity will be the same as the identity times A, which will be A. Again, provided the matrix multiplication can actually happen given the dimensions. Okay, so I know that seems a bit trivial, but we're getting to where that's useful. So inverses and determinants for 2 by 2 matrices. So when we given a square matrix A, there is going to be another matrix B. Well, not always, but most of the time. We'll talk about that in a minute. There is a matrix B such that A times B is the same as B times A, and it gives the identity matrix. So this is sort of equivalent. It's not the same as, but you can think about it a bit like the connection between A and 1 on A, for example. A times 1 on A is the same as 1 on A times A, and it just gives me 1. Okay. A times B is the same as B times A, and it just gives me the matrix equivalent of the number 1. Okay. It's a bit like, so let's put some numbers in that, 3 times a third, a third is the same as a third times 3, and it gives 1. So what we're talking about is the inverse of A will be the thing, sorry, I should have said that. If A times B is equal to B times A and equals the identity, then B is said to be the inverse of A. Okay, so if this property holds, then B is the inverse of A. Okay, and we call that A to the negative 1. Okay, so you've seen that with inverse functions, inverse sine, inverse cos, inverse tan. That should be familiar notation for inverse. So essentially we're saying that a matrix multiplied by its inverse is the same as the inverse multiplied by the original matrix, and in both instances we get the identity matrix when we do that. So it's a bit like us thinking about, a third and 3 as being inverses, because when we multiply them together we get 1. Okay. Alright, so we can verify this through a whole lot of algebra, which we don't have time to do, and we don't need to do it, because as I said, matrices is a very, very small part, and I'm really just trying to give you some background so that we can use them in the places we need to use them. So the inverse of matrix A can be found by solving this equation. Okay, so essentially what you can do, if you want to have a go, you do A, B, C, D, multiplied by some unknown matrix, which is going to be the inverse. So if this is A and this is the inverse of A, X, Y, Z, V, should have probably put those in a different order, but whatever it might be, and make that equal to the identity 1, 0, 0, 1. And if you expand all this out by multiplying and then equate, so just quickly let me do the top left, you do top row times left, so A times X plus B times Z, and that has to equal 1, 0, 0, 1, and so therefore, if these matrices are equal, that has to equal that. You form 4 simultaneous equations, you can solve the simultaneous equations, and eventually end up working out expressing X, Y, Z, and V in terms of A, B, C, and D, so that you've got the expression for the inverse matrix. As I said, I'm not going to do that, we don't have time for it. Okay, so maybe at some point in the future I'll shoot an offshoot video which goes through that algebra with you. So essentially, when we do that, we can discover that the inverse of A is going to be this matrix here. Now that looks a bit big and scary, but actually if we recognise that the denominators are all the same, we can factor that denominator out into a fraction at the front. So it's just 1 over AD minus BC, and then all that we've got left in the matrix is D, negative B, negative C, and A, which is what we've got here. Okay, so that value under there, that AD minus BC, that's something that we call the determinant, not to be confused with the discriminant, which we use with quadratics. Okay, so that value there, sorry, is called the determinant. Okay, and so the inverse of A is equal to 1 over the determinant, where the determinant is AD minus BC, and then it is this matrix here. So what we've got to be able to do is get from matrix A to the inverse of A. So we work out the determinant, which is AD minus BC, and then in the matrix, let's have a look at the key properties. On this diagonal, we've just switched those two values around on that diagonal, whereas on the other diagonal, that diagonal, the values haven't switched around, they've stayed where they are, but they've become negative. Okay. All right, we'll practice that in a second. A couple of other things to note. Only square matrices have inverses, and that's a bit to do with, the matrix multiplication has to be commutative, and so the only way you can switch the order around and switch the multiplication around and still be able to do the multiplication is if the matrices are square. By that I mean, if you've got a 3 by 3 times a 3 by 3, and you try and do that multiplication in the reverse order, you still have a 3 by 3 times a 3 by 3, so it's still possible. Whereas if you have a 3 by 3 times a 3 by 2, okay, it's possible in that direction, but when you reverse it, it's no longer possible. Okay, so they have to be square in order to have an inverse. Only square matrices have inverses. A square matrix only has an inverse if its determinant is non-zero. Okay, so obviously because determinant is down here in the denominator of a fraction, okay, it's all of these values are divided by that determinant. If the determinant equals 0, then the inverse doesn't exist. Okay, so a square matrix only has an inverse if its determinant does not equal 0. Okay, a square matrix is said to be regular if it has an inverse. So if the determinant doesn't equal 0 and it has an inverse, we would call that a regular matrix. If the determinant does equal 0 and it doesn't have an inverse, we would call that a singular matrix. Okay, let's practice find those things. So we've got the matrix A, which is 3, negative 6, negative 1, 8. Okay, and we first of all want to find the determinant of A. So remember, let's just get our general things. So if our matrix is A, B, C, D, if that's A, the determinant of A is AD minus BC, and the inverse of A is 1 over that determinant, and then we switch these values on this diagonal, so it becomes DA. We leave this diagonal where they are, but we make them negative, so that's negative B, negative C. Okay, so let's execute that for a numeric situation. So determinant of A is AD, which is these two numbers multiplied together, 3 times 8, minus BC, which is these two numbers multiplied together, negative 6 times negative 1. Okay, so it's just 24 minus 6, which is 18. Okay, so that doesn't equal 0, so therefore we can calculate the inverse, and we want to calculate the inverse, which is going to be 1 on 18, okay, And then in the matrix, we're going to switch the numbers on that diagonal, 8, 3. We're going to leave the numbers on that diagonal, but we're going to multiply them by -1. So they're already negative. When they get multiplied by -1, they're going to become positive. So that is our inverse. You can, if you want, put the 1 on 18 in. 8 on 18 is 4 on 9. 6 on 18 is 1/3. 1 on 18 and 3 on 18 is 1/6. But there's absolutely no need to do that. I would only do that if this was a fraction that multiplied into all of these to give whole numbers. Then I would say you haven't simplified. But if you're going to create fractions by multiplying it in, there is no need to multiply it in. Okay, process for calculating inverses and determinants for square matrices larger than 2 by 2 is really involved, and it's not part of this course, and we won't be looking at it. If you have a need to find an inverse or a determinant of a matrix larger than 2 by 2, so a 3 by 3 or a 4 by 4, you would use your CAS, but you will not have need to do that. Again, with your CAS, if you want to find its inverse, you just raise it to a power of -1. So there's the matrix to the power of -1. That will find the inverse for you. If you want to find the determinant, menu 7 for matrices and 3 for determinant, and then put the matrix in there. But if you just find the inverse straight away, you can probably see from your inverse that it looks like the determinant's probably 16, because that's the denominator of all those fractions. Once again, you probably won't have need to do that. Okay, let's get into how this applies to solving, sorry, no, we're not yet. We're going to talk about solving matrix equations and then look at how that applies to simultaneous equations. Okay, so we've learnt that addition and subtraction for matrices is very simple. Multiplying by a number is very simple. Multiplying two matrices is quite complicated. Dividing two matrices is impossible. Okay, so division is not an operation that is defined for matrices. It's impossible to divide by two matrices. So if we have a matrix equation, we can do mostly the same things as we do for an algebraic equation, except we can't divide. Okay, so if we had this very simple algebraic equation, we would first subtract 5 from both sides, and then we would divide by 2. Okay, if it was a matrix equation, we can subtract b from both sides, that's fine. But then we can't divide by a. Okay, so we need another strategy for division, and that's going to involve using our inverse, which is why we've talked about identities to lead to inverses so that we can now solve matrix equations. Okay, so if we revisit this algebraic equation, and instead of trying to divide by 2 at this next step, we think about it as multiplying by something that will cancel out the 2. So if we were to multiply by a half, that would make 1, and therefore we just get left with 1x, and so we've solved for x. And we do the same to both sides, and we can get to our answer via multiplication rather than via division. So we want to do that same thing. So remember, if we want to cancel this 2 out from here by multiplication, we're trying to think about, well, 2 times what makes 1? 2 times a half makes 1. Now, if we want to make the matrix equivalent of number 1, which is I, we know we can multiply by the inverse matrix. So in this situation, in the matrix equation, if we're solving this for x, we can subtract b from both sides, that gets us to here, and then we can't divide by a, but what we can do is multiply by the inverse of a. Now, we also need to remember that the order that we multiply matrices is really important, okay? So in order to get rid of the a from here, I'm going to have to put the inverse next to it, okay? So that means it has to go on the left-hand side. We have to multiply from the left. And so therefore, when we do the same thing to both sides, we also have to multiply from the left. The inverse must go in on the left-hand side there. So if it goes on the left, if you multiply from the left on the left-hand side of the equation, you must also multiply from the left on the other side of the equation, okay? So you can't just write, times inverse a over here, because that is a different thing to inverse of a times c minus b, because matrix multiplication is not commutative. We can't just do it in the opposite order and expect to get the same thing. Okay, whereas here with the numbers, we can multiply that by half on the right-hand side, and it's exactly the same thing. It doesn't make any difference, but it's not true for matrices. So we multiply by the inverse on the left from the left side on both sides of the equation, and in doing that, what we're really focused on is that. Okay, a times the inverse of a is I. and I times x is just x. So that's how we're going to get x on its own. So we've had to multiply by the inverse from the left here, we multiply by the inverse from the left over here, and so ultimately x is going to be inverse of a times c minus b. Okay, so as I said, we have to make sure that we multiply from the same side, so we've already talked through that. So if we had this equation instead, x times a equals b, and we want to solve for x, in order to cancel out the a, we need to multiply by the a by the inverse. And so we'd need to put the inverse in here to make that I, and x times I is just x. And so therefore we have to multiply from the right by the inverse, and it has to go from the right on the right-hand side of the equation as well. So we insert it on the right-hand side on both sides of the equation. Once again, that there is a times its inverse, which is going to give us I, and x times I is just x. So by multiplying by the inverse from the right, we are getting rid of the a essentially from the left-hand side, and we're ending up with x. And so therefore x is going to be equal to b times the inverse of a this time. Solving a matrix equation with your CAS, you can't just type in the equation and hit solve for x. Okay, you can't just do matrix times x equals another matrix and solve for x. So you really do have to be able to think this through yourself. You could, if you didn't just type x, if you actually made x into a matrix, and you'd have to think through the dimensions. So that's a 2 by 2 matrix. I'm going to multiply it by a matrix of unknown dimension to get a 2 by 1 matrix. Okay, so we know in order to be able to do the multiplication, those two numbers have to be the same, so that must be a 2. And we also know that these two numbers are going to give us our final order or final dimension, so therefore this has to be a 1. Okay, so it has to be a 2 by 1 matrix. So if you then actually set up a 2 by 1 matrix with a and b in it, and solve for a and b, it can do that. It just can't solve to find a matrix, it can find the individual values within the matrix though. Okay. Alternatively, and more efficiently actually, you do the rearranging yourself, the solving yourself, and work out that, to solve for x, I need to do the inverse of that 2 by 2 matrix multiplied by 411, or negative 411, and then you just type that in and press enter. You don't actually get the CAS to do the solving. You do the solving manually, you just get the CAS to do the grunt work of the multiplication. Okay, let's have a look through here. So we've got two matrices. Let's sort of put everything together a bit here. Two matrices, A and B, both 2 by 2 matrices. Part A asks us to find AB. So AB is going to be 3, 1, 1, negative 4, 2, negative 1, 5, 2. Let's multiply those together. So we're going to do top row times left column. So that is 3 times 2, which is 6. I'm going to write it down. Plus 1 times 5, which is 5. If you want to do that whole thing in your head, 3 times 2 plus 1 times 5, and just write 11 down straight away, great. But if not, just take a moment to write an extra step. Top right, top times right. 3 times negative 1 is negative 3, plus 1 times 2 is 2. Okay. Bottom left is going to come from doing bottom times left. And so we get 1 times 2, which is 2, plus negative 4 times 5, which is negative 20. Okay. And then the final combination, we're going to have bottom times right, and we get 1 times negative 1, which is negative 1, plus negative 4 times negative 2, negative 4 times positive 2, which is negative 8. And then that gives us 11, negative 1, negative 18, and negative 9. Okay, part B, we want to find the inverse of A. So our determinant is going to be AD minus BC, so that is 3 times negative 4 minus 1 times 1, so that's negative 12 minus 1, which is negative 13. So our inverse of A is going to be 1 over that determinant, negative 13, and we reshuffle the numbers by switching the numbers on that diagonal, so that becomes negative 4 up there and 3 down there, and leaving these numbers where they are, but making them both negative. So all fine. I am noticing that we've got a negative out the front and 3 negatives in the matrix, so it might be a bit nicer to write it instead as positive 1 on 13, positive 4, +1, +1, and -3. So you've just got the one negative. So essentially all I'm doing there is taking the -1 and multiplying it into the matrix. Multiplying everything by -1 gets rid of the -1 out the front and also changes the 3 negatives in the matrix into positives. Sorry. Okay, so there's our inverse. Okay, part C, find x such that ax equals b. Okay, so if ax is equal to b, to cancel out a, I'm going to need to multiply by the inverse on the left-hand side, and so I have to multiply by the inverse from the left on the right-hand side as well. Okay, and that then means that x is going to be the inverse of a times b. So I need to calculate 1 on 13. Inverse of a is 4, 1, 1, -3, and we need to do that times b, and b was 2, -1, 5, 2. Now, you can multiply the fraction in here, and then you'll have all of those numbers over 13, and then do all of that times that, but then you're going to have a lot of fractions. So multiplication, we're not changing the order of it, we're just choosing which multiplication we do first. We're going to multiply those two things together first. Also, we know the order of, we can multiply by a number at any time. Okay, we can do it first or after or whatever, and it's still the same thing. It's the matrix multiplication order that's important. So we're just going to multiply the matrices together while there's whole numbers in there, and then if we want to, we can put the 1/13 in later, or else we just leave it as 1/13 times whatever we get. So we're going to have 1 on 13. Let's see if we can do this all in our head. Top row times left column, so that's 4 times 2, which is 8, plus 1 times 5, which is 5, so 8 plus 5, which is 13. Oh, sorry, change back to the pen. Top row times left column, 4 times -1 is -4, plus 1 times 2 is 2, -4 plus 2 is -2. Okay. Oh, sorry, I lost that number up there. Should be -1. Bottom row times left. Okay, 1 times 2 is 2. Plus -3 times 5, which is -15. 2 plus -15 is 2 minus 15, which is -13. And then, sorry, just navigating my highlighters. 1 times -1 is -1, plus -3 times 2, which is -6. So we've got -1 plus -6, -1 minus 6, which is going to be -7. So you can leave it as that, or you can put the 1/13, multiply the 1/13 in, so that you get 1, -2 on 13, -1, -7 on 13. Either of those, this or this is fine. Okay, this time find y such that y times a equals b. Okay, so this time if it's ya equals b, we're going to need to multiply by a from the right hand side in order to cancel out the a there, and so it must, sorry, multiply by the inverse of a from the right hand side. So we must also multiply from the right hand side on the left. On the right, sorry. There's a lot of rights and lefts. On the right hand side of the equation, on both sides of the equation, we must multiply by the inverse from the right hand side. So y is equal to b times the inverse of a, okay? Which means b, which is 2, -1, 5, 2, yep. 2, -1, 5, 2. I'm going to multiply by that by a, which is 1 on 13 times, sorry, not negative a, by the inverse of a, 4, -1, 1, -3. Now once again, when we do the multiplication by the number, doesn't matter. So actually, it's easier just to sit that at the front. Again, focus on multiplying together the two matrices, and then we'll worry about the 1/13 at the end, or not worry about it. So we're just going to do the matrix multiplication. So we have 1 on 13, 2 times 4 is 8, plus -1 times 1 is -1, 8 plus -1 is 7. Top right, 2 times -1 is -2, -1 times -3 is +3, so it's -2 plus 3, which is +1, sorry. 5 bottom row times left hand column, 5 times 4 is 20, plus 2 times 1 is 2, so 20 plus 2 is 22, and bottom row times right column, 5 times -1 is -5, plus 2 times -3 is -6, -5 plus -6 is -11, 13 doesn't go into any of those numbers. I'm not going to bother multiplying it in. Okay. Alright, so I know that's a long video and there's quite a lot in that. I don't want you to get too bogged down in matrices. This is really all just about building up some background information. The solving matrix equations is the important endpoint. Next two videos, we're going to look at how we use that technique to solve simultaneous linear equations. So the work for today is from exercise 2E.